Let's conduct a hypothesis test from start to finish. A drug manufacturer markets a drug that helps on average 40% or more of the population that have the affliction the drug is supposed to help with. Now, the company has been receiving information from doctors that the proportion that are helped with this drug may be lower than company advertised. The test says the company gets a random sample of 980 patients with the affliction to test the drug, and it turns out that 355 are helped by the drug. Is there evidence that the company's advertisement is wrong? So now where to begin? It looks like this drug has been on the market. Their claim it's 40% or more, and that's what currently they're allowed to sell the drug because of this. And it looks like 40% is probably like a minimum. Like, so they're saying, look, 40% is probably the minimum. It could be better, but we're going to stick with that. So in that case, this becomes our parameter. And you can tell this is a proportion, so we're going to use P. And the null hypothesis will be that the drug helps 40% of the people that have this particular affliction. Now, why are we doing this test? Because there's now word from doctors that maybe this is not correct, that it actually might be lower. So we're going to still stick with the 40% because that's what this drug is being sold as. But what we're trying to figure out is this: is there any evidence on the alternative side that P is less than 40%? And that's what we're testing. Notice I'm using parameters here, P, it's parameter symbols. I'm making this parameter, the null hypothesis, equal to 40%. And I'm using the less than because what we're wondering about, it's the lower part. Greater than, we don't care. If it helps more people, that's fantastic. That's not a problem. Lower is a problem. What's my statistic? Well, since I'm using P, the accompanying statistic for population proportion is P hat sample proportion. And what is my sample proportion? It's 355 divided by 980. When I calculate this, I'm going to get approximately 0.36. I'm going to get more accuracy than that. Let me test this. That's just there for me right now, I guess, to get an idea. Yeah, 0.3622. Go forward here just to get a better idea, but I will enter the fraction when I use the final calculations. What's my effect size? Again, this is just going to be an approximation. My effect size is P hat minus P. I'm going to take the absolute value of this. So 0.3622 minus 0.4. Subtract the 2. What do I get? Approximately 0.03775. What does that tell me? This tells me that the difference between what I expected, so this is what you expect, and what I got, observed, is this amount. The question also becomes, is this difference important? And we'll talk about this later. Next, we'll get to the test statistic. Because we're using proportions, remember, we're going to just use Z. If you go look at your formula sheets, you'll notice that that is the test statistic, or the way we standardize values that are coming from the distribution of proportions. So we use a Z statistic to standardize this. And it's the same formula that we've been using. Minus 0.4. Divide this by the standard deviation. I have multiple fractions here, so I'm going to put one fraction for the numerator, and then the numerator has another fraction, so I'm going to click again. Type 385, no, 355. Divide this by 980. Minus 0.4. Take the square root. I'm doing this in decimals. Again, click the fraction symbol. 0.4, and I can do the other calculation in my head. 0.6 divided by 980. And there is my test statistic. The word test statistic is general. It applies to any type of test statistic when we're doing hypothesis testing or we're summarizing. So this could change depending on the situation. But the name is still, the general name is test statistic. Can I use a normal approximation to calculate probability? Because after all, what I'm about to calculate is a p-value. Is there evidence that the company's advertisement is incorrect? Well, the evidence is going to come in form of chance, a probability. So let's answer this question. Can I use a normal approximation to calculate probability? Which means, can I use the central limit theorem? CLT is what we're after. And again, the formula is this. N times P, N times 1 minus P. This must be greater than 10. Expected number of successes, expected number of failures. And I'm going to just use this value here. So we use an approximation. And 36% of 980 clearly is greater than 10. And if that's the case, this is going to be even bigger. Without having to do the calculation, the answer is yes. Yes, both of these values are bigger than 10. So what does that mean? That means I can draw a normal distribution. This is the distribution of all possible p-hats. It's a sampling distribution of proportions. Again, this whole thing is a sampling distribution of proportions. At the center of this is my null value, p equals 0.4. And what we're after is, again, I'm going to approximate it here. 0.366 is our statistic, which then, it lands on this side. Then I look at my alternative hypothesis, and what am I trying to show? That maybe this value is something less than 0.4. Well, at least our p-hat value landed on the side that may support this alternative. But I need to calculate this. This is going to be, this value, this probability is going to be the p-value, which is the probability of, and you can see the definition on the other page, the probability of getting a statistic as far away as the one we observed or even further away. So right now, this is as far as we observed, but this is the further away part. If this is correct, that's what a p-value is. So now the calculations look identical to what we did before. I'm going to just go p-hat, 0.36, z is less than negative 2.41. I'm not going to put all of them, but I'm going to type it in. And now we need to go to GeoGebra and figure out what this value is. I type my value here into GeoGebra. Let me choose the left, point to the left, that's the direction I'm headed in. And I'm entering negative 2.412587. 12587. Okay. And I get this value. 0.0079. And this is my p-value. What does this mean? And this is where you come in, the interpretation. Notice I need a lot more room. Here's what it's saying. If, I'm going to use more symbols to accept so much slope base. If the null hypothesis of the proportion being 40% is correct, and notice that that's what we used when we did this test, we're assuming this value is correct. So if the null, the null hypothesis of proportion being 40% is correct, then the probability of seeing a p-hat value or sample proportion as low as 0.3622 or lower, this is the extreme part, so the one we observed or even something lower is 0.0079 or 0.79%. Again, I'm multiplying this by 100 so I can turn it into a percentage. So this is not 79%, but less than 1%. And that is the meaning of the p-value. This is what the p-value means. So what does this number mean? That phrase. That's all it means. We're conducting something. This is a conduct hypothesis, which is called inference. This is a part of statistics that we call inference. What does that imply? Inference means to come to a conclusion based on facts, but not direct facts. Like I observe all of this, therefore I conclude that this is how I'm going to interpret all these facts. But it's not a direct connection, you're inferring. That's all the p-value means. The p-value does not tell you if the null hypothesis is correct or incorrect. It cannot tell you that. Let's think about 0.79%. How rare is this? How rare is 0.79%? Well, that happens less than 1% of the time. That's 79 out of 10,000. 79 out of 10,000 attempts, we would see a statistic as low as 0.3622 or lower. Again, that's all that means. So is it rare? You bet you it's rare. So what can we infer? Is there evidence that the company's advertisement is wrong? And the answer to this question is yes. Our result is unusual. If we assume the null hypothesis is correct. And so that must mean that maybe this assumption that it is correct is incorrect. And to make sense of this, look at the other page. So what's happening is there's two possibilities. Here is the result of some test, and the p-value is 0.03. And now we have to judge how rare this is, or what should we infer from this situation. And there's two possibilities. That we just happen to get unlucky and there's a rare event. That's one interpretation. The other part is that this value, which was what we conducted this hypothesis test, actually is not correct. And there's a other value that's actually, in this case, greater than the assumed value. And that's why we're observing. So the question becomes, why do we observe this value? If this null hypothesis is correct, one possibility is we got unlucky. Another possibility is that this is not correct. This one is correct. And then we did not observe a rare event at all. We observed a very common event when compared to what it actually, the null hypothesis should be, or the population parameter.